have script and more generally the design philosophy of script and contracts on a blockchain. And I'll give you a couple of script examples, how those are executed. What I'm not going to talk about is an exploration of the semantics of the script language. And I'm not going to give a description of all the common Bitcoin transaction output types. Why? Because you can look at those in a book. I don't think it's very useful to talk about the data structures or the code, but I do hope to give you a sense of what we think about when we think about contracts in Bitcoin. So I'll talk about why we have script. I'll talk about locking an output or a coin and unlocking it. I'll give a couple of examples of the stack for pay-to-pub-key and multi-sig. And then I'll just touch briefly on the role of a blockchain, whether it's computing or verifying. Okay, so why do we have script at all? In my first talk, I talked about digital signatures and using digital signatures to transfer coins from one owner to another. Why did Satoshi add script? Well, with those digital signatures, with a chain of signatures, that allows a coin to be moved from one person to another person to another person. But what if I want my coin to be spendable when 2 out of 3 people sign, right? So this might be an escrow service or some cold wallet service. How do I do that? What if I want my coin to be spendable when someone presents a secret or a secret value, for example, the pre-image to a hash digest? What if I want a coin to be spendable after a certain amount of time? What if, what if, what if? So instead of creating lots of different special transaction types, Satoshi added a generic scripting language. So users of Bitcoin could specify encumbrances or conditions for spending coins. Now that wasn't mentioned in the white paper, and it may be that script was added quite late into the development of the Bitcoin source code before release. Early versions of script were very buggy. For example, anyone could spend anyone's coins. That's a bit of a bug, which suggests that maybe the implementation was a little bit rushed. Okay, what is script? In Bitcoin, a contract is what we call a predicate. It takes some inputs and it outputs either true or false. And those inputs are the transaction and some additional data provided by the person spending the coin. And it returns true or false. True, the transaction is valid. This is a valid spend of the coin. Or false, the transaction is invalid. Contracts in Bitcoin are implemented as programs, and those programs are written in a programming language called script, which is an unfortunate name, but there we go. Script is a stack-based language, and that means that every item in that language either pushes elements onto a stack or acts on elements on that stack, either removing them or doing something to them, inspecting them in some way. And at the end of execution, if the stack is non-empty and the top element is non-zero, then that is true. Otherwise, the script is evaluated to false. Okay, so how do we lock a coin and encumber it with some kind of condition, and how do we unlock it? A transaction output is locked with conditions, and the input unlocks it by satisfying those conditions. The locking conditions are encoded in a script, which we call script pubkey. That's the name of the variable within the source code. And the unlocking proof or conditions are encoded in a script sig. Early versions of Bitcoin, so V0.1 up to 0.3.8, simply concatenated those scripts together and ran them, and if it evaluated as true, then that was a valid spend. Now, unfortunately, that's broken, and if you do that, anyone can spend anyone's coins. I won't explain why. It's quite a fun exercise to see if you can work out, once you know how script works, how you could spend anyone else's coins under this system. But it was broken. And so in V0.3.8, that was changed, fixed, by running the script separately. So first you run the script sig, and that places elements onto the stack. You leave those elements there, and then you run the script pubkey. Note that because the spender is providing the script sig, it doesn't really need to be, it doesn't necessarily need to be a script. It could just be placing elements onto the stack, right? So it shouldn't really be a script. It's just providing data elements. That's the script sig. So for example, here's an example locking condition. The simplest script pub key, the slides that I gave for translation said script sig. It should say script pub key there. I'll send out corrected slides. So the simplest script pub key is called pay to pub key, or P2PK. And the condition for spending a P2PK output is signing a message with the private key corresponding to the given public key. That message, the message that the signer must sign, is a part of the transaction that they are signing. And we talked about how digital signatures worked in the first talk. So this is just a digital signature over the transaction, or parts of that transaction. And incidentally, this is why it's called script pub key, because the script pub key contains a pub key, and script sig, because the script sig contains a signature. Okay, multi-sig is another very common type of transaction output, and a multi-sig is used when you want your coins to be encumbered with k out of n parties signing. So the condition for spending a multi-sig is that you must sign the message with k private keys out of the n public keys given in the locking script. And the message, public key, and the conditions for spending are providing a public key that hashes to that digest and a signature of a message with the private key corresponding to that pub key. Any questions so far? Does it all kind of make sense? All right, next up is pay to script hash. And pay to script hash locks an output with some arbitrary script. And you just provide the hash digest of that arbitrary script. And the condition for spending that is providing a script that hashes to that digest, plus the data required to satisfy the locking conditions on that script. Right, so the spender provides a script in this case. So why P2SH? Why do we do this? Why when we send a coin do we just use a hash instead of giving the whole script? Well, it means that the script pub key is a uniform small size. It's 32 bytes plus a bit of filler. And the sender, the person sending the coins, does not need to know the spending conditions for what they're sending. So if I want you to send to me, and for some reason I want the spending conditions to be I can't spend after some amount of time, or it needs to be a multi-sig, or whatever conditions I want to put on that output, you don't need to know about that if you're sending it to me. I just give you the hash of the script, and you send to that hash. The receiver, that's me who's put the conditions on, I pay the additional fee if it's a large or complex script. And the script pub key, because it's just a hash, it's a uniform template, it's hash plus some opcodes, that can be encoded in an address. We have an address format for pay to script hash. And then some newer ones, pay to witness pub key hash and pay to witness script hash. These are new locking conditions with SegWit, bit 141, which was in the last talk. Pay to witness pub key hash, pay to script hash. And these are similar to before, and the key difference is that the data required to satisfy the conditions is carried in a separate structure called the witness. That's why it's called segregated witness, and that witness is not covered in the transaction ID. That's what fixes the malleability. So those are all the common types of transaction output or script. I'm going to talk very quickly about two of those standard transaction types, and just show you what it looks like on the stack when we're executing those scripts. So pay to public key, this is the easiest, most straightforward transaction output type. The script pub key contains a public key, and that's 33 bytes if you're using compressed pub keys, plus the opchecksig opcode. And the script sig, that is provided by the person sending the coins. And first of all, you execute script sig. And because it's just a data element, that data element gets put onto the stack. So after you've executed script sig, you end up with a stack with a signature on, your script sig is empty, and you haven't done anything with the script pub key yet. Next, you execute script pub key. So the first element is pub key, that's a data element. You just push that onto the top of the stack. And then the next element in the script pub key is this opcode, opchecksig. That takes a look at the two elements in the stack and verifies that the signature is a true signature for that pub key. If it is, it pushes one onto the stack. And we're done. Now the stack is non-empty, and the top element here, 1, is non-zero, so that evaluates to true. Any questions about that? Okay, pretty straightforward. Multisig, again, quite straightforward. For a KFN multisig, the script pub key, so this is a locking condition, contains the number K, that's how many people I need to sign. That's 1 byte, usually. All N public keys, and again, those are 33 bytes each if we're using compressed pub keys, or 65 bytes if they're uncompressed. And then the number N, that's the number of public keys. And then opcheck multisig, that's another opcode, 1 byte. And the script sig, this is what's unlocking, this is what the spender provides, contains a dummy byte because there's an off by 1 error, and then K signatures, each of which are usually 71 bytes. So again, this is what our script pub key and script sig look like before execution. The stack is empty. So first of all, we execute script sig, and these are all data elements. So we see 0 at the top, we execute that by putting it onto the stack, and then sig1, and then sig2, right? So it's reverse the order. That's what it looks like after script sig execution. And then pub key execution, again, you've got a bunch of data elements. These all just get pushed onto the stack. So you get 2 pushed onto the stack, and then pub key 1 pushed onto the stack, and then pub key 2 pushed onto the stack. And then you have the opcheck multisig. That takes a look at all of the elements on the stack. It sees 3, it reads 3 pub keys, it sees 2, and says, okay, I need 2 signatures. Here are 2 signatures, and then it just accidentally picks up an extra element. That's the way it was implemented. And if these signatures are true signatures for some of these pub keys, then it pushes a 1 onto the stack. And that's what it looks like at the end of execution. Yep. Sorry, say that again? Yeah, this is bare multisig, and it's expensive because it's using up a lot of, it's using data in the UTXO set, so it costs extra fee to do this. Usually multisig would be wrapped into a P2SH. Yeah. Any other questions on that? Okay, so once that opcheck multisig is run, it pushes a 1 onto the stack. We're done with execution because we've drained our script pub key, and we're left with a 1 on the stack. So the stack is non-empty, the top element is non-zero, and so this evaluates to true. Any questions about that? Okay. I'm just going to finish with a kind of philosophical ramble about computing and verifying on a blockchain. So, as I said before, a contract is a predicate, right? It takes inputs and it outputs either true or false. And Bitcoin nodes, when they're verifying transactions in the blockchain, they're only interested in whether that contract evaluates to true. right? We're not interested in how it gets to true. We just need to know that the output is true and not false. Now, Bitcoin, the way it's implemented, uses script. Now, adding more computational workload to contract execution does not scale. It's a really bad way of scaling a blockchain. Verification is much easier and more scalable than computation, especially if we have things like aggregate signatures or batch validation for multiple signatures. If we have every contract is just some arbitrary program in some Turing-complete language, then that makes for an unscalable blockchain. So at the limit, a blockchain could use zero-knowledge proofs instead of script execution, right? So really, we just need a proof. We don't need the execution. But at the margin, there are lots of technologies in Bitcoin that can improve scalability by only committing minimal data to the blockchain, right? So instead of having the whole script on the blockchain or all of the conditions on the blockchain, if you can provide a proof that the conditions have been met, that's a lot more efficient, scalable. What are some examples of this? Well, only reveal the spending conditions at time of spend is good for scaling because it means those spending conditions don't need to be stored by every node before that coin gets spent. And we do that with pay-to-script hash or pay-to-witness script hash. Those are good for scalability because the UTXO set that every node keeps does not need to store the spending conditions of every coin. We can batch multiple payments into one on-chain commitment. So we do that with layer 2, things like Lightning. So one on-chain transaction for Lightning is encapsulating tens or hundreds or thousands of off-chain transactions, but we just finish with a proof that this is the final state, the final transaction. We could create a script where we only reveal the branch of the script or the branch of the contract that was executed. And technologies that do that are things like Mast or Taproot, which we don't yet have in Bitcoin, but maybe in a future soft fork we will have that. So if we have a contract which says we can spend these coins if condition A or condition B or condition C, instead of revealing all of those, we just reveal condition A with the proof that we've satisfied that. In the best case where everyone agrees, instead of showing a script, just broadcast a single threshold signature. Taproot and Graftroot are examples of doing that. And that's really efficient because if you just have a single signature, you can batch validate that with all of the other signatures in the block, for example, and it's really quick. You can combine multiple signatures into a single signature, so that's threshold. Signatures in Schnorr is very easy to do. And then you could embed additional conditions or commitments into a digital signature. Things like adaptive signatures and scriptless scripts do that. So it's no coincidence that these technologies that I talk about here, P2SH, Lightning, Mast, Taproot, Graftroot, threshold signatures, it's no coincidence that these are good for scaling, but they're also good for privacy and fungibility. Less data on the blockchain means better privacy for the people transacting, and transactions that look the same or uniform transactions are better for fungibility. So in conclusion, a Bitcoin output can be locked with a contract, so conditions on who's allowed to spend that output. And a contract is a predicate. It takes a transaction and additional data provided by the spender and returns true if it's a valid transaction or false if it's not. Bitcoin uses script to encode contracts and the witness data. So the witness data is this additional data that we provide to prove that we can spend or we fulfilled the conditions of that contract. And script is a stack-based language that executes on all nodes. So if you're a full node and you want to verify the transactions, you execute the script for all of the transactions. And finally, a blockchain is for verifying, not computing. We happen to use computing, script, but what we're really interested in is, are the conditions met? And that's verification. All right, any questions on that? Yes? Why is there no pay to witness pub key? Um, Good question. That was the way that SegWit was designed. There are two types of SegWit transaction: pay to witness pub key hash, which is 20 bytes, and pay to witness script hash, which is 32 bytes. Yeah, I don't know. The types of transaction that I've mentioned here are all standard transactions. So those are that's nothing to do with consensus. Any transaction is permitted that uses the script language, but those transactions won't get propagated by full nodes to miners unless they're standard. And there are now 7 types of standard transaction: pay to pub key, multi-sig, data, so op return, pay to script hash, pay to pub key hash, and now the 2 witness types. Yes, Taj? Okay. Pay to pub key hash is optimal in terms of weight. Yeah. Yeah, one advantage of pay to pub key hash is you don't reveal your public key until the time of spending. So pay to pub key is, in absolute terms, number of bytes smaller than pay to pub key hash, but pay to pub key hash aligns incentives better because it's better to have bytes in an input than bytes in an output. Any byte count to the signatures. So what Taj was saying is a pay to witness pub key, if it existed, would cost more because the weight, the adjusted cost of that transaction type would be greater than pay to witness pub key hash. Yep. Yes. So you can't have loops, for example. And the design philosophy behind Ethereum was that if you have a Turing complete language and if you have state saved on the blockchain, you can create many additional applications. Now, I'm not sure I agree with that approach. In fact, I don't agree with that approach for the reasons that I state here, that adding more computational workload to the blockchain does not scale. And even more, adding arbitrary workload, so adding a Turing complete scripting language where you can have any kind of computation does not scale. Now, the people at the Ethereum Foundation claim that they can make it scale with sharding and various other technologies. That's yet to be seen. But if you have a very simple base layer, Bitcoin, where it's really, in the end, just verifying signatures, that is a lot more scalable when you build on top of it with layer 2, things like Lightning and so on. No, script is not Turing complete. I have time for one more question. Yes. I cannot. All right, thank you very much.
All right, thank you again to John. And we'll just continue to the next session, which is by Greg.
Bitcoin used today. Okay. As John and I think Akio has mentioned, oh weird. Okay, hold on. It's not expressing the slide change. You know, like, do I have to click? Hold on. Maybe I just do full screen. No. Sorry. No, it wasn't at all. There we go. All right, addresses do not exist on the blockchain, but scripts do. So that's just one point that's already been mentioned a few times. And you've already seen these templates. Just going to go through it one more time with a few more facts and ideas. Pay to pub key. It was actually the first script template type. It had no address format at all. Does not exist. And it's not a special script. Like it's not evaluated in a special way. It's just a template, the obvious template Satoshi picked. Nodes would connect to each other over IP address with no authentication, and you get this script directly from the payee, and then you'd pay to that person, obviously and secure. And the only vestiges of it in the Bitcoin core code base is when you call generate in regtest, it puts the output directly in one of these. Not addresses, but scripts. And as noted before, we have this work. Is it reflective? It works. I think it's reflective. It's a screen. Doesn't work. Okay. Awesome. All right. Never mind. You have 33 or 65 byte pub keys and checksig, and the signature, which is DR encoded. Pay to pub key hash is actually the first address type, and on mainnet starts with 1. Base 58 encoding. Again, this is not special. It's just a template that was picked. It also introduces the idea of prop duped. The pub key is duplicated. Then it's repmd hashed, and then it's checked against the 20 byte pub key hash, which pushed on equal verify, and then that goes away, and then you do a check sig. Pay to script hash, it's the second address type that was standardized, starting with a 3 on mainnet. And the insight here is that the receiver is in charge of the spending policy. And so if you decide you want to have a very large, complicated script, like an 11 to 15 multisig or something like that, you should probably pay for it, not the sender. Previously, with a bare multisig, as John mentioned, previously with a bare multisig, the sender would pay for all this upfront cost, as well as on the blockchain as well. The UTXO size would be much larger. And if it goes larger than 520 bytes, it's an invalid push. Try to push it onto the stack, it'll be invalid. So you're limited to an N of 15 multisig script, which is the common limitation that people see. And this is in specifically in non-SegWit, by the way. So this is just legacy P2SH. It runs in 2 stages: the kind of the normal script execution, then recursively run again. So you have the script sig 0, the dummy input signature for this 1 of 2 multisig. Since John's already gone over the template, 1, you need one signature for these 2 pub keys. Then it pushes the entire serialized script on the stack, which is a non-zero value, so it's evaluated to true. It ends, and then it's recursively evaluated as the new script pub key is now, or the thing being evaluated in the stack is the script itself, this check multisig instead. Then it continues to evaluate as a multisig instead. Pay to witness pub key hash is the templated, so this is consensus templated way of paying to a single pub key. Has a Bech32 address, starts with BC1. It's longer than base 58, but more robust to errors, and you can even do error correction potentially, though it's not recommended for addresses specifically. And during script evaluation, so it's very simple here. You have the signature, the pub key in the witness. The script sig's empty, and the script pub key is 0 on the 20-byte key hash. So what happens here is that the 0 20-bit key hash is evaluated, and then the SegWit evaluation happens where it takes that 20-byte key hash and implicitly turns it into a pay to pub key hash script, and then is run again. So it actually goes through the op hash 160 steps. So it's what's called script code is identical. And there's a couple of script changes there, but mostly sig hash changes, things like that. Last, we have pay to witness script hash, which, so for this example, I do another one of two check multisig. So the script sig is empty again. The script pub key is 0, followed by a 32-byte push. It's also a replacement for P2SH, where we're hashing the script but doing it inside a stronger hash. P2SH only has 80 bits of security, which is deemed insecure in the nearest future. Bitcoin network does many more hashes frequently, like daily or something like that. So it's deemed insecure. And what happens here is the same way as before. 0 signature is pushed, and then the last element, which is the serialized script, is then evaluated as the script pub key, so to speak, within the actual SegWit evaluation. And I also don't mention the P2SH wrapped versions, which are more complicated, where for legacy reasons, the sender might not know how to send directly to a Bech32 address. So you wrap your pay to witness pub key hash or pay to witness script hash inside of P2SH. And so it's a kind of a nested loop, another nested loop of evaluation, which is a little bit messy, but allows for backwards compatibility. And this is all detailed. You can take a deeper look at this in the BIP 141 spec. It has examples and details, test vectors and just things you've already seen today, like BTC Deb by Callie and the BIP dot specs. And that's all I have. Thanks. Questions? Third time around?
Hi, my name is Brian. I'm going to be talking about SIGHASH no input. It was something that I was asked to speak about. It is currently not deployed, but it is an active proposal. So just really brief about who I am. I have a software development background. Just left LedgerX last week, so that's an exciting change in my life. The slides are gone now. Thank you. Also, I contribute to Bitcoin Core usually as a code review. All right, so in order to talk about what SIGHASH no input proposal is, I'm going to talk about SIGHASH flags. To talk about SIGHASH flags, this goes back to, I guess it goes back to how a transaction is structured, the data structure for a Bitcoin transaction. And in the script SIGs where you have a signature for proving that you have authorization to spend a coin, these signatures are constructed in a certain way, and there is actually a single byte appended to a signature that specifies in what way was the transaction signed. So there's a few different SIGHASH flags that are implemented and have been deployed since the beginning. The most common one that I use is SIGHASH all. That means sign everything except for the scripts. There are some others as well. SIGHASH anyone can pay is another example where you only sign a current input and then everything else in the transaction is not considered part of the signature. It's not covered under the commitment. So there have been many proposed improvements for these SIGHASH types where you say, well, maybe you only want to sign certain aspects of the transaction. And you could say, I'm interested in spending these coins under these conditions, but I'm also not interested in any of these other details which we're going to ignore. And so many different SIGHASH flags have been proposed for how to do this, including SIGHASH no input, but also others such as basically you'd imagine masking out different parts of the transaction. So any part of the data in the transaction that you can imagine, there's been a proposal for a SIGHASH flag for either considering it super important or completely irrelevant, and that you're fine with any sort of alternatives being proposed on the network without causing your signature to become invalid. So specifically SIGHASH no input, the way that this works is that the idea is that you don't actually care what specific input is being provided. You don't care what the transaction ID is that provides the input into the transaction. However, you do care about the amount. Very early on in 2015, this was actually proposed as a malleability fix before SegWit was proposed as a malleability fix. The problem, though, is that SIGHASH no input is actually somewhat dangerous, especially in the context of a malleability fix. So it was not selected by the community, and then we got SegWit. There is a proposal written, BIP 118, written by Christian Jacker. All right, well, this is a bunch of text about something called application-specific pub keys, which is basically such as the malleability fix, because it's actually quite dangerous. And this is because any input can be swapped into the transaction as long as it has a valid signature. And the signature with SIGHASH no input says you don't actually care about which input it is as long as the amount is correct. So specifically, SIGHASH no input has received recent attention because the Lightning Network developers would like to use it for something called watchtowers. And I believe there's either a Lightning talk today or tomorrow, and that will make more sense. But essentially, you want to be able to broadcast certain transactions to enforce the rules of the Lightning protocol. I already mentioned the malleability fix. There's also another Lightning Network proposal called L2, which is very confusing because Lightning Network is considered layer 2. So I think it was supposed to be a pun, but it's really just confusing. All right, so there were two other SIGHASH no input proposals. One was for an opcode, and then there was also one, I think, from Johnson Lau for his either script v2 or SIGHASH v2. I think that is possibly using like a bitmask approach. And so that's the overview of SIGHASH no input. I will be back later for other talks. Sorry, what? So you said it's only of what? Yes. So so SIGHASH no input is the idea that you only care about the value of the input. You don't care about the actual transaction ID. So the transaction ID is no longer a requirement under the signature. Yes, yes, the pub key has to stay the same, but otherwise it's identical. Well, anyone can choose the outputs that are going to be spent as long as they're actually valid according to the signatures that they're providing. So that's actually why it's dangerous, because if you were using SIGHASH no input in daily life, there was a slide back here. For like as your daily spending Bitcoin wallet, that's where things can get a bit dangerous. The issue here is that anyone with a signature can construct a different Bitcoin transaction that would still be valid. So it's not just, you don't have to just worry about miners, but also whoever you're giving this data to, like the Bitcoin transaction data. All right, thank you.
So that concludes our morning session for today, and lunch will be served here behind this secret ninja door. And or you can also go outside and get there's several restaurants and stuff around the place. Make sure you come back before 1:25, where we'll continue the next session. Thank you.